Thank you for your introduction. Hello everyone. I'm going to talk about our work called stereo consistent screen space reflection. In this work, we address three inconsistent cases: inconsistent screen space geometry, fitting boundary, and reflection sample. To explain where these inconsistent cases come from, I first give a little background. Nowadays, global illumination is usually used to enhance the user's realistic experience. In real-time rendering, screen space reflection is a widely applicable global illumination algorithm. After acquiring the G-buffer, stochastically sample array, and merge in screen space, we can cheaply get the reflection results. But what happens when using screen space reflection in stereo rendering? There are several inconsistent cases present. One significant issue arises from geometric inconsistencies. Let's begin with the red eye. We perform screen space reflection in the red eye and obtain the correct result. However, in the left eye, if the reflected surface lies outside the view cluster, the screen space reflection result will be incomplete. We refer to this issue as the outside view problem. In another case, the left eye can correctly capture the reflection. But the reflected surface is occluded in the red eye. We refer to this issue as the occlusion problem. These issues stem from inconsistent geometry. Next, let's consider another inconsistency concerning the flattened boundary. In this case, both views can capture information from the reflected surface. In screen space reflection, the blur field is typically used to mitigate the edge color of artifacts. However, if we calculate the field level separately, inconsistent boundary can introduce severe visual discomfort. The third inconsistency concerns the sampling of the reflection. Screen space reflection correctly renders the reflected surface visible in both eyes. However, to maintain real-time performance, only one or two reflection rays can be traced per pixel, and some ray may be mishit. This introduces significant noise. Even with a spatial temporal filter, the inconsistency in noise can still greatly affect visual comfort. Overall, we have identified three types of inconsistent cases, and our goal is to mitigate these inconsistencies and achieve consistent reflection results in stereo rendering. Let's first take a look at the inconsistent screen space geometry. Due to the different visibility of geometry between the eyes, screen space reflection diverges significantly across different views. Our key observation is, can we use another view's screen information? The answer is yes. When tracing reflection rate in screen space, we can align the visibility of both views using consistent geometry. Now the question is, how to achieve consistent geometry? For a set viewport case, we implement boundary detection. For example, we initially trace rays in the left eye. If a ray reached beyond the left eye boundary but remains within the right eye, we continue tracing in the right eye. This is called as boundary detection. In case of occlusion, we employ dual detection to handle occlusion from different instances or cell. Initially, we address occlusion by different instances. We traverse ray in the right eye. However, after 3 steps of ray matching, the reflection ray becomes invisible in the right eye. Currently, Utilizing screen space information from the left eye enabled continued rematching. Next, we address self-occlusion of the surface. Initially, we trace the ray in the radar. After 3 steps of matching, the reflection ray becomes invisible in the radar. Utilizing the stereoscopic screen space geometry, we continue rematching in the left eye to obtain the reflected surface information. Here, we define 3 types of depths: instance front depth, instance back depth, and re-reached depth. If the re-reached depth exceeds both instance front depth and back depth, we traverse ray in another eye. This method is termed dual detection. With both boundary detection and dual detection, we achieve stereo-aware traversal and minimizing the additional overhead injury traversal. We compared our result with those obtained without a traversal model. Our approach provides more accurate information and maintains better virtual consistency. Next, let's take a look at the inconsistent field boundary. Due to differing field levels between the eyes, reflection near screen boundaries can become highly inconsistent. Within the traversal model, we ensure stereo geometry consistency and can merge the frustums of both eyes. Employing a uniform field is a good choice to achieve consistent field boundaries. So, how to get a uniform field? We perform screen space reflection as usual and obtain the coordinates of the reflected surface in stereo or screen space. For naive field, each eye computes the field level separately, which leads to inconsistent field effects. In our stereo-aware field, we use the point closest to the screen center in PL and PR to determine the field level. We compared our results with those obtained without a field model. Our approach preserved more details and maintained consistency between both eyes. Finally, let's take a look at the inconsistent sample. Due to the random nature of sampling and the low sampling rate, reflection can exhibit significant inconsistent noise. The motion vector-based method increases sample count by reusing temporal information to mitigate the noise result. Here are some methods to calculate the reflection motion vector. It's predictable that by reusing binocular information, we'll achieve more consistent results. Therefore, the main question is how to find relevant pairs in stereo rendering. There is a true boundary from reflected surface PO to V1, where S1 is the screen coordinate. Inspired by glossy motion vector, we find the virtual image PO prime. Then we project PO prime to V2 and obtain S2. The pair of points S1 and S2 is referred to as the reprojection point pair. Now we can reproject samples between stereo views. Firstly, the left and the right eyes independently perform screen space reflection to capture reflected samples. Next, we project the sample from the right eye to the left eye to reuse stereo information. Typically, such a projection is viable primarily in pure specular case. However, each pixel on the screen corresponds to geometry information from an error after spatial filtering, so we can directly reproject samples. At this stage, is the reprojection truly reliable? The answer is no. We have found the reprojection introduces new artifacts in the following 2 cases. In case 1, when the virtual image is occluded, the reused information from V2 is incorrect. In case 2, when the reflected surface in V1 differs from the reflected surface in V2, the reused information is also incorrect. We compared our results with those obtained without a reprojection model. Our approach maintains stability and consistency between both eyes. Specifically, we verified the effectiveness of the incorrect reuse fixed model. With the fixed model, ghosting artifacts were clearly eliminated. Next, we'll present our results, user studies, and an exploration of our method. First, we'll compare the results of screen space reflection and our method in the room scene. Our method demonstrates significant improvement in consistency along fit boundaries, with the additional cost of 0.83 milliseconds. The second comparison is in the one scene. Our method achieved better and more stable reflections. The third comparison is in the pink scene. In complex occlusion scenes, our method obtains more accurate and consistent reflection information. Lastly, we conducted a comparison in the temple scene. For complex textures, our method achieves more accurate and consistent results. We also conducted an equal sample comparison between our method and the traditional equal sample screen space reflection. Despite increasing the sample number, screen space reflection still fails to resolve inconsistent stereoscopic cases, where our results demonstrate greater consistency and closer alignment with the ground truth. Additionally, we conducted 3 user studies with 10 participants using the Pico 4 Enterprise Edition device. The first study focused on visual quality. Participants view mirrored rendered results using a VR headset and rate their experience. Most users found that our method provides better visual quality. The second and third study are inconsistency study and ablation study. We presented the image side by side for users to rate them based on stereo vision. In the inconsistency study, our method achieved higher scores compared to the screen space reflection. We conducted a significant test, demonstrating that our method significantly outperformed screen space reflection. In the model ablation study, our showed that each model in our method improves user visual consistency. Our method has some limitations. Firstly, when reflective surfaces are occluded from all points, the reflective information may become unreliable. Secondly, when reflective surfaces are outside all view frustums, reflective information may be entirely missing. Lastly, some original issues of screen space reflection remain unresolved. We have proposed 3 consistent methods for using screen space reflection in stereo rendering. Our method minimizes the increased overhead while maintaining consistency. Additionally, it is easy to implement in existing renderers. In the future, we'd like to consider temporal information to enhance its stereo vision. It would also be interesting to explore the application of our method with forwarded rendering. Furthermore, other screen space algorithms such as chromatic aberration and SSGI could be extended to stereo rendering. Thank you for your attention, and I'm happy to take any question now. My English is not good, so I hope everyone can speak slowly.